we're continuing on with our discussion from a couple of days ago. And that is, we were starting to talk about the dualistic nature of matter. And so we discussed this idea of the dualistic nature of electrons, bringing in the concepts of James Clerk Maxwell, Albert Einstein, and then this idea of Louis de Broglie, where we can say that all things that have a mass and are in motion, have a speed, will emit some kind of a characteristic wavelength. And we ended our discussion at that time with this Professor Dave Explains video. And I wanted to replay a section of this video because, again, it is kind of important to our overall discussion here. So,
Professor Dave again, let's take a look at the Schrodinger equation. Professor Dave again, let's take a look at the Schrodinger equation.
He knows a lot about the science stuff, Professor Dave Explains.
Through the work of Planck and Einstein, we were forced to accept that energy is quantized, and that light exhibits wave-particle duality. Then de Broglie extended this duality to include matter as well, meaning that all matter has a wavelength, from a tiny electron to your whole body to a massive star. However, an object's wavelength is inversely proportional to its mass. So objects bigger than a molecule have a wavelength that is so tiny that it is completely negligible. But an electron is incredibly small, so small that its wavelength is indeed relevant, being around the size of an atom. So we must view electrons as both particles and waves from now on. Therefore, we must discuss the wave nature of the electron. So what kind of wave might this be?
sorry about that.
An electron is incredibly small, so small that its wavelength is indeed relevant, being around the size of an atom. So we must view electrons as both particles and waves from now on. Therefore, we must discuss the wave nature of the electron. So what kind of wave might this be? We can regard an electron in an atom as a standing wave, just like the kind we learned about in classical physics. Except that rather than something like a plucked guitar string, an electron is a circular standing wave surrounding the nucleus. If we understand this, it becomes immediately apparent why quantization of energy applies to the electron. Because any circular standing wave must have an integer number of wavelengths in order to exist. Given that an increasing number of wavelengths means more energy carried by the wave, we can see the Bohr model for the hydrogen atom begin to emerge as...
All right, so I want to stop it right here and just kind of point out something that was kind of glossed over, but is important to us to understand. Notice that we are given energy levels for each of these. Now, the model he's showing isn't expanding based upon the energy level. It's not getting further and further from the nucleus. But what we can see is that if we count, what we get in the fifth energy level here is we have 5 wavelengths. 1, 2, 3, 4, 5. And in those 5 wavelengths, we can see that our frequency has changed from where it was before. And if that goes now to 9 wavelengths, see that now we have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 waves, 9 wavelengths. In roughly the same space, our frequency has shrunk. And according to our relationship between wavelength and frequency and energy, a shorter wavelength, higher frequency wave is going to have more energy. And so that's why if we go from the 5th energy level to the 9th energy level, we are going to need to have a subsequent jump in energy to turn that lower frequency wave, not light, but matter wave of electron, to a higher frequency matter wave electron at the higher energy level. And that's where that quantization comes in. We have a certain amount of energy at this spot, we have a different amount of energy at this spot. The only way to bridge that gap is to absorb a photon equal to the energy of the gap.
A standing wave with 1 wavelength, and then 2, and then 3, and so forth. This is the reason that an electron in an atom can only inhabit a discrete set of energy levels. The circular standing wave that represents the electron can only have an integer number of wavelengths. When an electron is struck by a photon of a particular energy, this energy is absorbed, promoting the electron to a higher energy state and increasing the number of wavelengths contained within the standing wave. This is why the electron goes to inhabit a higher energy level, and this is what is fundamentally occurring during electron excitation.
And so that's where we stopped at the moment in time. Again, if you watch this video through the rest of the way, you will see in here that it gets into some talk about constructive and destructive interference, which gets into bonding, which we're really not ready to talk about yet. And then
we can certainly discuss.
It later gets into something called the Schrodinger equation. And the Schrodinger equation is kind of at the heart of what we're talking about today. Because the Schrodinger equation, this mess of calculus and partial derivatives here, ultimately tells us something very fundamental and important about electrons. So these questions here about describing the position and motion of an electron, these come down to something fundamental that does not get a whole lot of praise or talk, and that is the Heisenberg uncertainty principle. The uncertainty principle says basically that we can't know both of these things at the same time. The more we know about its position, the less confident we can be about its motion. And the more we can describe its motion, the more we can try to hone in to detect it, the more difficult it's going to be ultimately to figure out where exactly it is. Now, Heisenberg's uncertainty principle does have an equation associated with it. We're not going to get into that equation either. But we can talk about one of the fundamentals that kind of integrates both of these, and that is the concept of atomic orbitals. So the Schrodinger equation allows us, if we actually solve the Schrodinger equation, what we get is a three-dimensional object out of that Schrodinger equation that tells us a rough probability of where the electron is. And so that works in the same kind of way that the uncertainty principle does, in the sense that instead of saying the electron is right here, we can say with the Schrodinger equation and with the three-dimensional shapes that are predicted by the Schrodinger equation, the electron is somewhere in here. Can't tell you exactly where it is, but chances are really, really, really good that it's somewhere in this space. That's what an atomic orbital is. And so from that perspective, atomic orbitals give us these three-dimensional shapes. They solve the Schrodinger equation for us. And depending upon what kind of energy is going into these electrons, we can actually get different types of orbitals. And so the orbitals we describe are based upon their shapes, and their designations come as a result of those shapes. So for example, s orbitals. S orbitals are spherical in nature. They have no angular dependence on their orientation. So because they are spherical objects, because they are basically balls, doesn't matter which direction I hold that sphere, all of the orientation is going to look exactly the same. Some things to know about s orbitals. First, they exist in every energy level. They are kind of the lowest energy sublevel of any energy level. And that's why they exist in every single one. They're always spherical in shape. And the last thing that we can say about them is that their size increases with their energy level. So we can see here that our 1s orbital is very, very small. It's tight, it's compact, it's very, very close to the nucleus. As we go from 1s to 2s, we're going to see an increase in size. As we go from 2s to 3s, we're going to see an increase in size. And this would be true the more and more we expand from that first energy level. The second type of orbital is something called a p orbital. P orbitals have some key characteristics to them that are interesting. First of all, they're dumbbell shaped. What you have there are two kind of spheroid nodes that are lobes that are connected. The space in the middle, it's hard to see in these drawings. I'll try to highlight it here for you. But the space here in the middle that exists between the two axes, these are actually what are referred to as nodes. And nodes are places where there is no chance of finding an electron. So in between each of those spheroid lobes, you have a node, and that node in between is a place where we're not going to find electrons. And so each p orbital features at least one of these nodes. Now, as we go from 2p to 3p to 4p and so on, we'll find that more of those nodes actually exist. But at minimum, we have one in each one of these p orbitals. P orbitals do have an orientation. They are oriented toward the x-axis, the y-axis, and the z-axis. So this is the px orbital here at the bottom. It has its lobes directly oriented on that x-axis. The p sub y orbital has its lobes oriented on the y-axis. The p sub z has its lobes oriented around that z-axis. Some other things to note. There is no such thing as a 1p orbital. There's not actually enough space for that to exist. And p orbitals are the second lowest energy sublevel in any energy level overall. So s orbitals will always be present. P orbitals will usually be present in a given energy level. The only one that isn't is again the 1p. The first energy level is very, very small. It only has room for the 1s orbital to exist. All of the other orbitals, sublevels, just cannot fit in there. It's just too close to the nucleus. With the p orbitals starting in the second energy level, we find that they are second lowest in energy. And so for that reason, they are fairly common, and we see them in every energy level other than the first. D orbitals, now we start to get into some more complex kinds of ideas. If you can kind of rationalize and think about it, what we have effectively done in each of the cases here is if I start with an orbital, let's say that there's my s orbital. If I were to draw a line down the middle here and establish a node in that kind of way, what I would have ended up with as a result is the separation of those two lobes would ultimately give me a p orbital. If I take this and cut it in half, I end up with these two lobes that represent that p orbital just like that. For the d orbital, it's kind of the same representation again. This time, however, instead of cutting it vertically, I'm going to cut it horizontally. And that horizontal cut is going to result in, now I have four lobes. And among those four lobes, I also have two nodes, one in the horizontal, one in the vertical. And that is essentially what a d orbital is. So we've gone from no node s to one node p to now two noded d. And so from that perspective, we are getting more variety here. We are getting more interesting kinds of configurations. What can we say about d orbitals? Most of them have a clover leaf kind of shape. The 3dz squared, the dz squared here on the far right is kind of the exception to that rule. It is double noded, but the double node is kind of in an odd spot around this little interdimensional plane here. Other things that we can also note, there are 5 possible d orbitals, each with a different 3D orientation. These are high energy. They only start to appear in 3rd energy level. And again, we see a greater level of complexity. And with that, at least 2 nodes per orbital showing up here. Now, there is one other type of orbital that is possible. It is called the F orbital. The F orbital, if we kind of follow through the logic that we've gone through here, where we go from no nodes to 1 node to 2 nodes, the F node does have 3 nodes. That 3rd node is by basically cutting in the 3rd direction. The 3rd direction would be the interdimensional plane that exists in what would be the wall of the computer screen that you're looking at. And so what we end up getting for most of the d orbitals are these 8-lobed dragonfly kind of oriented pictures. F orbitals are extremely high in energy. We only see them used in very, very specific circumstances. And even at that, most of the time they're relatively useless to us. Unless you're doing some work with rare earth chemistry, you're looking specifically at the lanthanides and the actinides. Most of the chemistry of the F orbital containing substances and elements is just not, it's not terribly useful to us. So we're going to kind of gloss over it here. Acknowledge that they exist. We could give you an idea of roughly what they look like. The basic gist of it is that these would be kind of offset. So the pink lobes are actually behind the blue ones. And that's how we would have to show it. So not terribly easy to draw or see, but that is essentially what it would end up looking like. So again, the Schrodinger equation gives us these orbitals, gives us these 3-dimensional shapes with which to look at and to view and to start to interpret. The main point, what we're going to get into today, is looking at something called a quantum number. Now, quantum numbers, there are 4 quantum numbers that can describe any given electron in an element in an atom. Quantum numbers are a series of 4 related numbers that give us the energy, the shape, the orientation, and the spin of any given electron in an atom. And so what I want you to kind of think of is each one of these quantum numbers goes from incredibly general information and gets more specific as we go from quantum number to quantum number to quantum number. So at the top end, this is the hierarchy on which we are working. The energy level is described by So our energy level is described by what is called the principal quantum number. The sublevel is going to be described by the angular momentum quantum number. The orbital that it's in is going to be described by something called the magnetic quantum number. And then the actual electron is described by the spin quantum number. So again, each one of these gives us a level of specificity that increases as we go from left to right. So the most generic quantum number is the principal quantum number. The principal quantum number tells us the energy level in which the electron that we are describing is residing in. Now, the principal quantum number is a whole number integer. As we've seen, energy levels start at 1 and have the capability of going all the way to infinity. As we talked about in our lecture on Friday, infinity kind of describes when the electron has actually left the atom. But before we get to infinity, we can technically describe energy levels that go all the way up to that point. And understand from what we saw in the Professor Dave video, all that energy level means is how many wavelengths are crammed into that circular wave. And so the more that we cram in, the higher energy it is, the further it tends to be away from the nucleus. So we move on then to talk about the angular momentum quantum number. Angular momentum quantum number, L. This is an interesting one. This is going to tell us the sublevel in which our orbital or our electron resides. So within every energy level, there are sublevels. There is the S sublevel, that is the lowest energy sublevel. There is the P sublevel. Those are the dumbbell-shaped orbitals that are kind of next in energy. There is the d sublevel, which have those cloverleaf orbitals that are kind of high in energy, and then it gets more and more energetic from there. The value of L tells us which of those sublevels is actually being utilized. Now, the value of L is defined, at least in terms of its boundary, by the principal quantum number. So if my principal quantum number is 1, then there's only one possible value for L, and that is 0. The maximum number of energy level, or excuse me, the maximum number of sublevels in a given energy level is equal to the value of n. And the value of L starts at 0 and goes all the way to n minus 1. Now, that doesn't mean that orbital values exist and we have to choose the one that is equal to n minus 1. So if I'm in the third energy level, my possible values, if n is equal to 3, L can be equal to 0, 1, or 2. Those are the possibilities. The third energy level contains an S sublevel, a P sublevel, and a D sublevel. Which one that electron is in depends upon its energy and would be described by one of those 3 quantum numbers, not all 3. So if it is in a P, if I am talking about a 3p sublevel, that means that n is equal to 3 and L is equal to 1, because the value of L does dictate the sublevel. If my L is equal to 0, I am describing the S sublevel. If my L is equal to 1, I am describing the P sublevel. If my L is equal to 2, I am describing the D sublevel. If my L is equal to 3, I'm describing the F sublevel. Now, again, there are more values of L that are possible. These are the 4 most common because those are the ones that actually have electrons in them when electrons are in the lowest energy states possible. And again, we really don't see the F ones show up until we hit those rare earth elements. We're talking about periods 6 and 7. So those tend to be kind of irrelevant. But understand that if the criteria of the first 2 are met, meaning n is a value that is an integer, and L is a value of an integer that is at least 1 less than n, then technically that is a possible sublevel. And we need to take that into consideration. It might be in an excited state, it might be a high energy state that electrons only get to when they absorb a certain photon of light. But it is technically a place where an electron could exist. So that's angular momentum. Magnetic quantum number and spin quantum number. Well, these, again, we're getting into more and more specificity. So a magnetic quantum number would actually tell us which of the orbitals in that sublevel that electron resides in. So values of the magnetic quantum number are bounded by L. They go from negative L to positive L through 0. Spin quantum number, on the other hand, is very simple. Every single orbital within a sublevel has a capacity for 2 electrons. Now, those 2 electrons can only exist in 2 different orientations. We call them spin up and spin down. Those are the 2 possible orientations for spin quantum number: spin up and spin down. Spin up is this one, positive 1/2. Negative 1/2, on the other hand, that is considered spin down. And so, with those 4 quantum numbers in mind, now we can state something else, and that is something called the Pauli exclusion principle. The Pauli exclusion principle says that in an element, in an atom, no 2 electrons can hold the same 4 quantum numbers in the ground state. Because while we may have several electrons in a given energy level, and we might have up to, depending upon the sublevel, 2 electrons in the S, 6 in the P, 10 in the D, 14 in the F. Even with all of that, by the time we get to the orbital level, there are only 2 possibilities. And if we describe its spin, we are differentiating between those 2. One of those is going to be spin up, one is going to be spin down. So the Pauli exclusion principle says no 2 electrons in an atom can have the same 4 quantum numbers. And that's because if we are at the lowest energy state possible, it's impossible to have 2 electrons in the same orbital pointing the same way. They both have, if they're both spin up, then that means that one of them is in an excited state. And it would have to go back to spin down to get to its normal state. All right, any questions so far? All right, so let's go through and do some practice problems with regards to quantum numbers. The first, what are the names of all of the subshells in the n equals 4 shell? Again, shell is another way of saying energy level. So if we're at n equals 4, that means that the possible values of L could be 0, because there's always we always start at 0. L could be 1. L could be 2. Or L could be 3. Those are the 4 possibilities. Remember, every single energy level has an equal number of subshells within it. So the 4th energy level would have 4 subshells within it. The names of those subshells, well, L equals 0 is the S sublevel. L equals 1 is the P sublevel. L equals 2 is the D sublevel, and L equals 3 is the F sublevel. So the names of the 4 subshells would be S, P, D, F. How many orbitals are in all of the subshells at this particular level? Well, for that, we have to go back to our definitions, back to our drawings. The S sublevel only had one orientation. The P sublevel had 3 orientations. The D had 5 orientations. The F had 7 orientations. Now, if I didn't know that, what I could also look at is, remember, our magnetic quantum number, m sub L, tells us that the number of orbitals, because it tells us the number of possibilities. We're going from L positive to L negative. Well, if L is 0, I only had one option there. That was 0. And if L was 3, I had if L is 1, I had 3 options. I had the -1, the 0, and the +1. If L was 2, I had 5 possibilities, ranging from -2, -1, 0, +1, and +2. And if I had L is equal to 3, I would have had 7 possibilities. Ranging from -3 all the way to +3. So my quantum numbers, again, this is a model that we use to help us to rationalize what we know to be true about orbitals and electrons. And so how many orbitals are in this n equals 4 shell? Well, I had 1 here plus 3, that's 4, plus 5 more is 9, plus 7 more, 16 in total. So 16 total orbitals in the 4th energy level. With each orbital capable of holding 2 electrons, that means we had 32 electrons that are possible in the 4th energy level. That doesn't mean all 32 are going to go in there. That just means that that is its capacity. All right. Any questions with this one? All right, a couple more here and we'll call it a day. What are the quantum numbers that would be used to describe a 5D orbital? Well, we aren't told anything about the 5D orbital's orientation. So based on what we know its energy level and its sublevel, D. We know it has an energy level of 5. We know it has a sublevel of D. Energy level is the principal quantum number, so that's n equals 5. Sublevel is the angular momentum quantum number L. D corresponds to a value of 2. So those would be the 2 values of the quantum numbers. We don't know anything else about it, so we can't go any further with it. That's all we would need to put for a question like this. 5D, 5th energy level, D sublevel, 5th energy level given by n equals 5. The D sublevel is recognized by L equals 2. That's it. That's all you need to do. So what are the values of m sub L? What values of m sub L are possible for a 4f orbital? So we have a 4f orbital. And that tells us that our energy level is 4. And our sublevel is f. Well, from a quantum number standpoint, energy level is the principal quantum number, so n would be equal to 4 in this case. Sublevel would be the angular momentum quantum number. The value for f for angular momentum is 3. And so that's the important thing to kind of keep in mind here is that sublevel and angular momentum quantum number are talking about the same thing. So there's a very specific value of angular momentum that is corresponding to this particular sublevel, the F sublevel. And so the last thing that we do is to answer this question about the magnetic quantum number. M sub L values range from negative L to positive L, going through 0. So we need to go from -3 through 0 to +3. That would mean that our values are -3, -2, -1, 0, +1, +2, and +3. All 7 of those would be possibilities for orbitals within that sublevel. Now, we're not told which one it is, and actually, even if we knew, there would be no guarantee. There's no fixed correlation between, oh, well, -3 is actually the dxy orbital. That's not specified anywhere. But it does give us an idea of its relative position.